The recent observations of Comet 3I/Atlas mark a particularly important moment in the study of interstellar objects, offering astronomers a rare opportunity to examine material that did not originate within our own solar system. Using the powerful Discovery Telescope at the Lowell Observatory in Arizona, researcher Qiqing Zhang captured a striking new image of the comet as it moved away from the Sun after completing its close pass. The image shows the comet glowing an intense green and appearing, at first glance, to lack a visible tail. While this might seem unusual or even concerning to a casual observer, scientists emphasize that these features are not only normal, but scientifically valuable clues about the comet's composition, behavior, and orientation in space. Comet 3I/Atlas is especially significant because it is an interstellar visitor, meaning it formed around another star system long before drifting into ours. Unlike most comets, which originate in the Kuiper belt or Oort cloud, interstellar comets carry chemical and structural signatures from environments beyond the Sun's influence. When such an object passes through the inner solar system, it provides a fleeting but powerful window into planetary formation processes elsewhere in the galaxy. Every observation, therefore, becomes critical, particularly during periods when the comet is active and interacting strongly with solar radiation. As comets approach the Sun, they undergo dramatic physical changes. Their solid roe or nucleus is composed of a mixture of frozen gases, water ice, dust, and complex organic molecules. When solar heat reaches the surface, these frozen materials begin to sublimate, transitioning directly from solid to gas. This process creates a surrounding cloud known as the coma, which can grow to tens or even hundreds of thousands of kilometers across. The coma reflects and emits light, making the comet visible from Earth and allowing astronomers to analyze its chemical makeup using specialized filters and spectroscopic tools. In the case of Comet 3I/Atlas, the coma appears brightest when observed through a green filter. This green glow is a common feature among comets that venture close to the Sun and is strongly associated with the presence of diatomic carbon, known as C2. Zhang specifically used a filter designed to isolate this emission, revealing that the comet contains a substantial amount of carbon-based material. Many of these materials exist in the form of hydrocarbons, large molecules made primarily of carbon and hydrogen, which are thought to be relics from the early stages of planetary system formation. When these hydrocarbons are exposed to intense ultraviolet radiation from the Sun, they begin to break apart in a process similar to photodissociation. Zhang compared this effect to the way ultraviolet light damages human skin cells, leading to sunburn when proper protection is absent. In both cases, UV radiation has enough energy to disrupt large, complex molecules by breaking chemical bonds. On the comet, this process results in smaller molecular fragments, including pairs of carbon atoms bonded together. These diatomic carbon molecules are particularly efficient at emitting green light, making them relatively easy for astronomers to detect even from great distances. The green glow, therefore, is not an indication of anything unusual or dangerous happening to the comet. Instead, it is a sign that the comet is behaving exactly as expected under solar heating, actively releasing and processing material from its nucleus. In fact, the brightness and structure of the coma can tell scientists a great deal about the comet's composition, activity level, and even the physical properties of its surface, such as how porous or layered it might be. One feature that initially caught attention in the new image was the apparent absence of a dust tail. Comets are famously associated with long, dramatic tails stretching across the sky, so seeing a comet without one can seem strange. However, the lack of a clearly visible tail in this case is largely a matter of perspective rather than physics. Zhang explained that the dust tail is still present, but it is oriented almost directly along our line of sight from Earth. When a tail points toward or away from the observer, it can become difficult to distinguish from the coma itself, effectively hiding it in plain sight. Careful inspection of the image reveals subtle asymmetries in brightness within the coma. The left side of the comet appears slightly brighter than the right, a clue that the tail is curving gently behind the nucleus and just off to one side. This uneven glow is consistent with a tail viewed nearly head-on, compressed visually into a small region rather than stretched out across the sky. Such viewing geometries are common in comet observations and are well understood by astronomers, even if they can be misleading to the untrained eye. Understanding these geometric effects is especially important during what scientists refer to as a critical observation phase. After a comet passes around the far side of the Sun, it often re-emerges into view under different lighting and orientation conditions. This period allows astronomers to compare pre- and post-perihelion behavior, assessing how much material the comet lost, whether its activity increased or decreased, and how solar heating may have altered its surface. For an interstellar comet like 3I/Atlas, these comparisons are invaluable, as they may reveal how such objects respond to a stellar environment different from the one in which they formed. The Discovery Telescope at Lowell Observatory plays a crucial role in this work. Its combination of light-gathering power and advanced instrumentation allows researchers to isolate specific wavelengths of light and study faint, fast-moving objects with high precision. By using narrowband filters tuned to emissions like those from diatomic carbon, astronomers can effectively map the distribution of different molecules within the coma and trace how they evolve over time. This kind of detailed chemical analysis would be impossible with the naked eye or even with smaller telescopes. Beyond the immediate scientific findings, observations like these also contribute to a broader understanding of how common certain materials are in planetary systems throughout the galaxy. The presence of hydrocarbons and carbon-based molecules in an interstellar comet supports the idea that the basic building blocks of organic chemistry are widespread in space. This has implications not only for planetary science, but also for astrobiology, as it suggests that the ingredients for life may be readily available in many stellar environments. It is also worth noting that comets are dynamic and often unpredictable objects. Their activity can change rapidly depending on their distance from the Sun, rotation rate, and internal structure. Jets of gas and dust can suddenly turn on or off, altering the appearance of the coma and tail over short timescales. Continuous monitoring during key phases of a comet's journey is therefore essential, particularly for rare interstellar visitors that may never return. In the end, the green glow and seemingly missing tail of Comet 3I/Atlas are not signs of mystery or malfunction, but rather natural consequences of chemistry, physics, and perspective. The observations captured by Zhang and his colleagues demonstrate how much information can be extracted from subtle details in light and shape, and how careful interpretation can turn an initially puzzling image into a rich scientific story. As the comet continues its journey out of the solar system, the data collected during this brief encounter will remain, helping scientists refine models of cometary behavior and deepening our understanding of the wider universe from which this small, icy traveler emerged.